there's going to be an after party from 5 p.m. to 8 p.m. at the platform. So make sure you guys go ahead and attend that. It's a good networking event. You know, there's going to be snacks. So go make sure you attend it. All right, now hope you guys are ready for more machine learning and AI talks. Now we have Miss Eleni Strolia. She's a professor in the Department of Computer Science at the University of Alberta. Um, and her research focuses on addressing industry-driven problems, adopting AI and machine learning methods to improve and automate tasks. Moreover, she was recognized with the Killiam Award for Excellence in Mentoring, and she has supervised more than 60 graduate students and PDFs who have gone forward to a stellar academic and industrial careers. And since 2020, she's the director of University of Alberta's AI for Society signature area. And now I'm gonna give the stage to Miss Eleni, and she's.
So it's a great opportunity for me to be here. Can you hear me? Yes. I am vertically challenged. Okay. Thank you. That's good. So what I want, it was great to see the previous presentation talking about really highly technical problems and performance. What I'm going to do is quite different. I'm going to tell you 3 little stories about research projects that I have been involved with, and all of which they exemplify the opportunities that we have to transform data into something useful, an insight that can change the way we do things and the way we behave. So let's start a little bit about artificial intelligence. Like, I want to give you a high-level view of what is the scope that I'm considering when I'm talking about artificial intelligence. Every activity today is mediated through software. We're all using our mobile devices. There are sensors on the highways. There are sensors in the natural environment. There are sensors in the cars, and we know much about traffic. So all our activities and all our designed artifacts are embedded with sensors that generate data streams. And through the leaps and bounds of progress that we have made on cloud-based architectures and storage and computational resources, we are now able to store this data, where that was not possible until fairly recently, I don't know, 5, 10 years ago. Now, having this wealth of data has made us able to apply data science and machine learning algorithms on this wealth and large scale of data in order to construct models. So machine learning and data science at a very high level are transformation processes that take data that are describing instance phenomena and construct high-level abstractions, models that cover all of these example phenomena. And these models can be simulated and used to predict the future, or they can be used to classify phenomena in different categories. And these predictions and simulations can be embedded to new software that can change processes. So understanding how cars drive on a highway can control traffic lights. So this is the complete cycle that we're interested in, and the types of problems that I have been involved with cover something and everything in this pipeline. So I just want to give you a little bit of another high-level view. Canada has identified 5 different areas of strength and interest in research and technology, and one of these areas is technologically advanced Canada. And if you read the elements in technologically advanced Canada, there are 12 points, and 3 points, at least 3, but more refer to AI type of activities. But 3 of these points are artificial intelligence, machine learning and deep learning, human emotions and language applications, including indigenous languages, surveillance, and computer vision. And one of these projects that I will be talking about focuses on surveillance through social media platforms, where surveillance has some interesting connotations, but I want you to think about what does it mean if we understand what people do and say on social media? What can we learn? And how can we use what we learn to actually help people and improve the state of affairs in the world? One of the other 12 points is big data and analytics, which is really the focus of this conference. And my work, the story that I will tell you on that point relates to Internet of Things and smart buildings. And the last point is about smart and digital manufacturing using embedded sensors and 3D printing. And I'm kind of stretching this definition a little bit to include the sensors embedded in our cell phones and the ways they can be used for supporting psychiatrists and clinicians, help people develop and maintain their mental health. So these are the three stories. These are the three key points that fall under the technologically advanced Canada. Okay, so let's start with social media. The project I'm talking about is called AI Buzz, and it involves people from engineering. The lead is Dr. Liane Lefsrud, people from computing science, myself and Dr. Barbosa, business, Joel Gammon, he's with the University of George Washington University in the States, and our industrial partner is CECN, the Canadian Energy and Climate Nexus. I should also mention that all the projects that I'm talking about are interdisciplinary. There is no single discipline that can address any of these things, and they all involve partners from the real world, whether they are community stakeholders or whether they are industry partners. So if you look across Canada, there have been several pipeline projects, extraction and mining projects that have been cancelled, all of which have had substantial financial costs. So understanding the conversation around energy, especially in Alberta, is of interest to our partner CECN. So what did we do? Our problem, our intent, was to understand the speakers. What are people talking about when they talk about energy, when they talk about energy companies, when they talk about oil sands, when they talk about economy in Alberta and the words diversification come to mind? How do they feel when they express their opinions? And how these conversations relate to the various provinces and geographies and possibly political leanings of people. So the practical objective, the second objective, was we wanted to have large open data sets in order to enable public research in Canada. Research in social media is something that is of huge interest, and it has very interesting legal implications. I understand in the United States, you can collect any data you want. In Canada, we typically do not use the complete data, but rather the IDs, and therefore every individual researcher has to rehydrate the data. So that's an interesting perspective on the legalities of these problems. And what can you do with Twitter? We'll focus on Twitter because it's the easiest one to access with its APIs, but we're doing work with Reddit and now Telegram, which is slightly the same, slightly different. Nevertheless, what can you do? You can do lexical analysis. You can look at the words that people use, and the words are very interesting. Why? Because linguists have developed a whole lot of vocabularies where they understand the meanings of words. We'll come back to that. So there are vocabularies that help people understand personality values, personality traits, personal values and personality traits, sentiment and humor. So if you understand the sentiment polarity of a word, then you have an insight on the sentiment that is expressed by the tweet. You can also do morphological analysis. You can look at whether somebody is using links to individuals, hashtags, whether they attach media, whether they have long tweets, whether they have grammatical tweets or simply keywords. So this structure of the language of the tweets is what I refer to as morphological analysis. Then you can cluster both tweets and users. So if you look at all of these various properties and cluster users into groups that are similar, internally similar and far away from each other across groups, and then you can try to recognize what are the various groups representing, what constituencies they represent. So that's another element. And then you can try to do regression analysis to look at some phenomena. I'll get to that very briefly. So we want to look at trends and patterns. How does the conversation change over time? And we want to do these groups and recognize and predict what they might be talking about in the future. So a quick sideline on organizational and behavioral psychology maybe. There are different ways and different theories that recognize people's humans' values. And human values are important because they kind of drive the way they think. They are underlying the way we form opinions about phenomena. And in this project, we wanted to know if we can recognize clusters of users talking about different things and having different sentiments, can we recognize their underlying values? So we adopted this framework of human values, and it describes 12 or 10 different values, and they're organized in 2 dimensions. In one dimension, you can see that some values focus on the self and some values focus on society. And in the vertical dimension, you can see that the values are either growth and open and sort of extroverted, if you want. And on the other side, we have stressed values that express stress and fear and inward looking. So pretty much these 12 values fall into this two-dimensional space, and every one of these values comes with a set of words. So there's a vocabulary that associates words with one of these values. So when we look at the tweets, we can see the words and we can recognize what value they most likely represent. So this is the tool that we built. Tweets come in and we do 3 different types of analysis. The first is lexicon analysis. So we take every single word and we compare it against a different vocabulary. So we have dictionaries for personal values, dictionaries for humor. So you look at a word and you know if it is very funny, not funny, or in 2 categories in between. Sentiment, positive or negative, and also a different dictionary that actually recognizes the emotion expressed, as in joy, disgust. And the last type of dictionary is a domain-specific dictionary that talks about energy and climate. Then the morphological analysis refers to recognition of how many hashtags and what types of hashtags, handles of other people's, emojis, and URLs, references to other links and media and audio-video attachments. And the last aspect of the analysis is public influence measures. So there are standard mechanisms that measure essentially the engagement and the potential reach of a tweet, primarily based on the followers of the user and the actual responses to the tweet, the quotes, the likes, and the replies. So we know something about the structure of the tweet, the syntax if you want. We know something about the meaning of the words, and we know something about the impact of the tweet. And as you can imagine, we're trying to figure out what kinds of tweets have what kind of impact. That's at least our goal. We're getting there. So here's an example. We have multiple data sets, but a good one, a biggish one, is the what we call Energy East. It has about 150,000 tweets between 2013 and 2021. And of these, about 30,000 are original tweets, and they are all retweeted a lot, and there are tweets with quotes and replies. So this is the data set that we're looking at. And if you look at the timeline of these tweets, then you see there is a big peak here. Suddenly, the conversation is getting hot. And what happened? This is October 5, 2017. It is the cancellation of the Energy East pipeline. Now, of course, everybody knows what happened then, but if you are here and you see it, you see that the conversation really heats up when important events happen. And obviously, this is a good event to talk about, but there are all these other peaks that are also interesting, and we're digging through them. But let's look at this. What can we see? Well, we can see a little bit of what is the conversation about. So looking at the week before, like the days before and the days after, we see that these tweets have a much higher density of personal values expressed. And we have a bit of analysis of basically how frequent the various personal values are, and they're all about achievement, self-direction, and power. These are the top 3 personal values. Now, we still don't understand what this means. So it could be achievement in a negative way. You know, we just missed an opportunity to achieve something, or it could be achievement. Yes, we canceled the pipeline. And we looking at the positive and negative effects of the conversation, we can see it was slightly more negative than positive, but kind of balanced. And looking at this analysis, this very sort of polar conversation, like 50-50, black and white, is an interesting phenomenon. It's not that frequent in our timeline. Now, trying to dig a little bit better into what types of people are talking, we looked at about 30,000 users. So we looked at the tweets and we compiled user profiles by collecting all the tweets of a user. And we used the new language models. I hope all of you are familiar. I'm going to give you a very bad definition of language models. So basically, word embeddings, the place of word in the context of other words is called a word embedding. And if you look at everything that has been written, if we could look at a very big data set, we can construct these word embeddings and basically count how frequently words go together. And words that go together appear close in a multidimensional space. So with this very bad introduction to word embeddings and language models, let me tell you that we used GLOVE, and we used 50 dimensions of GLOVE, and we basically analyzed the words that people are talking about, and then we clustered these profiles. And we ended up with about 8 clusters. Agglomerative clustering tries to put things together that are close, and you keep on going and connecting them until you find a place where the clusters, if you join them anymore, the clusters will become incohesive. So we ended up with 8 clusters, and here they are. We looked at them. So now we have the clusters. We started reading what do people say in these clusters. So the first one is primarily talking about Justin Trudeau, and it's primarily right-wing and against Justin Trudeau. The second one is climate change activists. The third one is not as specific, not about climate change, but more generally, we thought it looked left-wing. The fourth one was focused on the economy. Then we have French and Spanish. So these are not really meaningful clusters, but they are linguistically distinct. And then we have the cluster that we couldn't classify, and then leftovers. So now you look at these clusters and you have a little bit of an insight in the meaning of what people are talking about. And if you look at these clusters and the positive and negative feelings, you start having an idea. Now, none of these correlations are very statistically significant, so I don't have results to present to say that, you know, all the right-wing people were speaking negatively about the event, but these are the types of things that we're examining now and trying to extract and dig into. So that's the first story. The second story is about smart buildings and Internet of Things. So this is, again, interdisciplinary work. We have people from computing science, we have people from electrical and computer engineering, civil engineering, and medicine. I just want to talk about medicine in particular. People who are interested in health are very interested in smart buildings. Now, everybody understands that healthy air is a good thing for health after COVID, but more importantly, the way you place vending machines and what you sell in the vending machines and the way you place elevators and stairs in a building actually change the way people live in a building. So there is a very strong angle in actually designing buildings in a way that will encourage movement. So that's very cool to me. Okay, I hope the role of computing science and engineering is kind of obvious, so I'm not going to expand on that. But here's what we're doing. Today, every commercial building is designed using a building information model. So the owners of the building do not get a 2D diagram of how the building is going to look like. They get a 3D model in a visual tool, and on top of the visual, there is also a logical structure of the floors, the rooms, the doors, the windows, and even the electrical systems and all the other sensors that are embedded. And fascinatingly, this model dies. You see it, you use it to develop the building, and then it's not used anymore. But what could you do with it? Well, a lot of cool things, it turns out. Okay, we're not going to do that. I'm going to talk about it. So, what can you do with that? We are working with the UCommons building. The UCommons is a building at the University of Alberta. It is 100 years old, and it's been renovated. So I'll use this just to show you a little bit the UofA campus. So, 100 years old, it's got to get changed. We have embedded in it a whole lot of occupancy sensors. We have an HVAC system that is monitored. All the controls of the HVAC system are monitored. And there is this BMS protocol that sends information about the status of the pumps and the heats and the valves into a central repository. And we have a battery, and we have solar panels, and we have a microgrid controller. The microgrid controller decides what source of energy will be used. We'll be using utilities, we'll be using the solar panels, or the battery. And it turns out that I believe, I'm almost 100% sure that the University of Alberta is charged according to the peak amount of energy that we spend. So if you can bring the peak a little bit down, lots of savings are to be obtained. So our objective here is to predict consumption, monitor consumption, predict future consumption based on environmental factors and actual usage, the schedule of the building, the classrooms, the types of offices that it has, and control and discharge the battery ahead of time in order to reduce the peak and therefore have savings financially. But also you can imagine if we can best use solar panel energy and reduce reliance on the utilities, then we'll also reduce greenhouse emissions. And now we have a very measurable way of actually figuring out what this change can do, because we can control actually half of the building, and the other half is sort of our control case study, and we can see the energy consumed by the two halves, one controlled by machine learning and the other controlled as usual. So I want to talk a little bit about the design of the buildings. Right now, the design of the buildings is an activity that is handled by architects in consultation with the occupants of the building. Right now, we're holding stakeholder meetings and we're designing things. But we have developed an algorithm, which is essentially a search algorithm that designs rooms automatically based on constraints. And the rules and the constraints that we use are ergonomic constraints, that are preferences of the owners, and you can basically build automatically something like that. This is an experiment with kitchens, but we're working with living rooms and family rooms in residential buildings, and we're just starting to apply it in office spaces. And therefore, what you can is you can have multiple alternatives that are demonstrably better given the rules that you're relying on, but you can also give options to the occupants and have them choose and give feedback to this process. So our current project is looking at how to change user feedback into models. That's my alarm that I should be paying attention to my slide progression. However, what we are doing now is we're learning from examples. Up until now, our rules come from ergonomics, from codes, ergonomic preferences with architects and decorators, but now we're trying to embed people preferences. What do they like better? And this is, again, a machine learning problem where people design spaces, and then we extract rules from this design process. We have also used these models to run simulations to predict virus transmission rates in different uses. If you remember, during the pandemic, people were talking about separating schools and have half the students go Monday, Tuesday, keep Wednesday empty, and then the other half would go Thursday, Friday. So we have run simulations to see what would this mean, because if you increase the time of the day that people stay in the class, because the Monday, Tuesday would have to be almost longer in order to cover the whole week, but you reduce the density, does it impact the transmission? And what we can do is we can run basically simulations of how people move in the space and how likely it is that they will meet each other and for a long time that might involve viruses transmissions. And then you can see what the potential effect will be of the two alternative designs of using the building and choose what is best. Okay, I'll skip that slide and I'll give you a very high-level teaser about computational psychiatry. This is a huge group at the University of Alberta, and you can imagine that medicine and health has a whole lot of data from labs and from medical imaging. But what I'm interested in is the cell phones. Cell phones are capturing much of the information of our behaviors and our activities, where I'm going, how much I'm moving, when I'm moving, and they capture voice. And voice is one key indicator of both of mental health and cognitive health. So I'll tell you about one single paper. There is a huge range of papers here, and we focused on Alzheimer's dementia. So we had data collected from people who had and did not have Alzheimer's dementia, and the data set was the individual describing a picture of a mother cooking and her kids stealing cookies from a cookie jar, and the cookie jar was falling. So this is the picture that was presented to every individual, and every individual is describing what's happening, and the audio is about 2, 3, 4 minutes. So this audio was the data samples that we used to analyze, and we did two things. First, binary classification. Does the person have or not Alzheimer's dementia? And then we tried to actually estimate the MMSE score. MMSE goes from 0 to 30, and the higher, the more likely it is that you have dementia. And what we can do, let me show you a little bit the pipeline, how this works. You get the audio recording and you extract a whole bunch of acoustic features. This is basically the tenor of your voice, there are many standard features, the spectrum that you're using. We're extracting language and fluency features. So basically, if my sentences are syntactically correct, if I have lots of hum, pauses, if I stop for a long time, if there is prompting happening from the person showing me the image. And of course, we have the ground truth from a questionnaire, that is the MMSE questionnaire. So we have the value of whether you do have or not dementia, and the features. And we built acoustic models, language models, and we put them together. And this is the work that gave us 85% accuracy, recognizing people having or not dementia, and an MSE score of 5.6. So basically, root mean square error. If 30 is the value that we're playing with, 5 is kind of close, is small relative to 30. It's not as good as you want it, but it is a good indicator for somebody to go through this test and then present that to their clinician. So, with this pretty fast view of everything, I want to leave you with a very vanilla statement, which I hope that I have given you evidence. People talk about data being the new oil. And what does this mean? It means it's valuable, but it actually also means that there's a whole lot of processing that needs to happen in order to refine it and make it valuable, and there's a lot of linking that has to happen with data from multiple streams in order to actually have valid models and valid intuitions that will be useful to actually do some work. And this work has been supported to a degree or other by AI for Society, which is an umbrella for people that are interested in real-world problems using machine learning and AI techniques. And I believe this is the way to actually conduct this type of research through multiple types of expertise, all coming together, driven by the need to address specific problems with real-world solutions. So thank you for your interest. Let's see. Hopefully you have some questions, and hopefully I left you some time to give me a good challenge. I saw one hand here and one hand there.
Yeah, hi, thank you. Thank you for your presentation. Really interesting. So quick question about the last experience on the Alzheimer. Is that kind of a test that is available for public? So let's say if I want and double check.
It's not that good to unleash to public. Okay. So no. But if anybody's interested, we're working with clinicians that are basically working with Alzheimer's dementia. So they are participating in our studies, and we are trying to deploy other more real-world studies as opposed to these standard data sets. So we're working with people who are using it, but in a research context, not clinical.
Okay, yes. Thank you. Another quick question. So going back to the first case, so did you guys have the opportunity to double check that, or kind of test it with the same model already, kind of a different question?
We have worked with the tweets of Jason Kenney, with a political scientist, Jared Wesley, and we actually have a paper coming out on recognizing mental health disorders in English and Spanish speakers on Twitter. It's actually fascinating what you can see, how good classification you can get, between 80 and 60% for 9 different disorders. So surveillance on social media is very useful for many different phenomena. Thank you for asking that. I forgot to mention it. So I saw one question, 2 questions there, so you go ahead.
Okay, so I wanted to go a little bit deeper into the Alzheimer's disease thing as well, because with MMSE specifically, this is more related to Alzheimer's dementia, which is the later stage of the disease. Have you looked anywhere into this, like how good this methodology could be for diagnosing early stages of Alzheimer's disease?
The answer to your question is no. We're relying on standard data sets. We, in fact, did just another challenge with English and Greek data from different pictures. The results are slightly worse because we trained in English and we applied on Greek. So we are working with standard data sets collected, and we really don't have much control of who are the people. So, no.
Because with MMSE, there's a cognitive test, of course. So
yeah.
It's when you see cognitive decline in those patients that you will be able to measure things. But there's a very large group of people who have Alzheimer's disease but have not reached the cognitive stage yet.
Yes. Oh, it's really a very difficult problem, because when we looked at actually the people speaking, they have dementia, they're classified in dementia, but they sound perfectly fine to me. So the MMSE score is very difficult to use as a label in such a short 2-minute description. So you're absolutely right. And one last question, I hope.
So I was really intrigued by your Twitter analysis. So I just had a small question regarding that. The lexical analysis that you guys did, what kind of regression, I guess, machine learning algorithms you used for the sentiment? Was it like CNN, RNN?
No, we did not actually use classification. This is the lexical analysis, simply counting words. So there are linguists who have said, here is a dictionary, and the word joy is happy. So joy is associated with +1 sentiment, And that's what we're doing. We're basically counting the number of words, the frequencies of words that are associated with different labels, and this is the frequencies that we're reporting in these trends. We have not done much good analysis. We use this for classifying in depression, and it was not very useful. The actual words were not actually terribly useful. There we did use deep learning models, and we used all the words. The labels of these dictionaries were not great.
And for just as a follow-up question, for the Alzheimer's analysis, regarding the voice data, what kind of, did you guys use classification methods for those?
Yes. So basically, for the voice data, we used random forest, we used SVM. I think random forest was pretty good, but really, you need the combination of these pauses, like the fluency measures, not really the meaning of the words, because we're doing English and Greek and German. So the meaning is not there, but the syntactic structure, the mix of whether you have nouns and verbs, these are the high-level language features that elevate the result to 85. Just acoustic data for Alzheimer's, I think the best we got was, 72%.
Okay. Thank you for that.
Thank you. So I would be happy to talk with anyone more. I realize that I'm just eating on the next speaker's presentation. So thank you so much, and looking forward